Hello everybody, this is Dr. Dave with Physics 152. I want to talk to everybody today about capacitors. So what exactly is a capacitor? A capacitor is a device that is built to store electric charge separation or electric charge difference. We're going to understand that statement a little bit more as things go on. But the first thing is I want you to know how we represent these in a circuit. There are generally, we show them as being parallel plate capacitors, even though in reality most capacitors aren't parallel plates. They use similar elements of this design. We always show them as if they were parallel plates just because it's a diagrammatic representation of them. So capacitors basically always have the same length sides on them. Batteries are generally shown so that one of the sides is longer than the other. This often leads to a lot of confusion with students. Sometimes we will draw a battery as such, showing that there are multiple pieces in here, so you cannot confuse that with a capacitor picture. So we draw a schematic representation of our circuit as follows. We've got one side longer than the other. This is my battery, positive here. Then I have a switch, and now I have a capacitor. And your book talks about this in the reading. It lets you know that this is a schematic, meaning this is not a literal interpretation of how it's drawn. It could have long wires, short wires. It could have a lot of different arrangements. So this is the electrical connection, meaning that the positive end of the battery is connected to one end of a switch. That switch controls the ability for current to flow into the capacitor, out of the capacitor, back to the battery. So what happens when this switch is closed? Well, if we have ideal wires, and ideal wires for us means that we have no potential drop over these wires. When we learn about electrical resistance coming up here, we'll understand that ideal wires also mean that we have no resistance in these wires. So our battery here will have one end that's positive, one end that's negative. And if you've done high school chemistry, you might have seen electrochemical cells in which you had maybe copper on one side and zinc on the other side and some kind of acid that dissolved them. That's the model of battery we're thinking about here. We're thinking about an electrochemical battery or maybe a power supply, something that keeps a constant or a steady voltage difference across them. So if you know what a AA battery is, or a AAA battery, or even a C battery or D battery, all of those batteries have the same potential difference across them of 1.5 volts. So just to be clear, a AAA battery has a 1.5 volt potential difference. A D battery, right, which is a much larger battery, has a 1.5 potential difference. So the question is, what's the difference between a AAA and a D? The difference is the amount of current that they can supply. So what we've got here is a battery. We don't know exactly what kind it is necessarily, but it keeps a constant potential difference. That is, as charge flows from it, the potential difference of this doesn't change. Conversely, however, the capacitor does change. The charge separation across the capacitor isn't the same over time. So what we know happens, right? We know that electrons are the things that are moving. However, when we determined our conventions of what was positive and negative, we didn't know what the moving charge particles were. And by the time we found out, it turns out we were backwards and it didn't matter. So in reality, electrons leave the negative end of the battery heading towards the positive end. And this trip is interesting with the capacitor. The negative charge leaves this end, comes over here to the plate because it's found a path to get back here. It gets this side of the plate and it can't cross this gap. Right? This is a physical gap that it cannot get through. So that negative charge arrives in this plate and it begins to repel other negative charges. Well, the other negative charges on the plate can't go anywhere on this side. However, on the other side of the plate, the negative charge that's like sitting right here can leave, right? It can leave from repulsion and head back to the positive side of the battery. Well, because this was neutral to begin with, when the negative charge leaves, it leaves behind a positive charge. So what do we say happened? We say a negative charge leaves the negative side of the battery, comes on over here to the plate, pushing away another negative, back to the positive of the battery. Now what do we say is that's what we call electron current. We also have what we call battery current, or our conventional current. In our conventional current, we think of positive charges flowing out. Even though they don't really do it, we can think as if they did. So a positive charge leaves this side of the terminal, comes on over, deposits on the plate, pushes the positive that was here away, leaving behind a negative charge. But that's not all. Over time, this continues to happen. and you begin to build up more and more and more charges, one charge at a time, pushing away the other charges. Now you see this in the simulation that we had, and that is, this depiction I have here is a very simple 2D depiction. But now if we look at the simulation you saw in your worksheet, or your problem for this week, you see that the charges spread out fairly uniformly on this plate, and then the charges spread out on the bottom plate as well. And so you end up building, right, a rather strong electric field pointing out across here. Now it's important to remember that if you add up all the charges here and all the charges there, that it's still an electrically neutral device. But we say that the capacitor is charged. So what we mean by that is the capacitor has built a charge separation of positives on one plate, negatives on the other plate. And this charge separation is going to create an electric field. Well, last week in our homework we learned that if you follow the electric field over some distance, that leads to a potential difference. So if we follow this electric field over this distance d, we're going to get a potential difference across here. So it's this electric field that wasn't here when the battery wasn't connected that is now storing the energy there. So let's talk about capacitors a little bit more. What do? They store charge separation. They store charge difference. And one common point of confusion that people have is they think capacitor or capacitance means capacity. This is not true. And it is a point of confusion. You might think that the capacitor is the amount of gas you can have in your gas tank. That's not the case. It is instead telling you about its capability to store charge based on a potential difference. Let me show that to you in graphical form. So let's imagine you have two different capacitors, capacitor C1 and capacitor C2. Well, if I have two different capacitors and I put this amount of potential difference over them, what we're going to see is that C2 is going to store less charge than C1, which will store more charge for the same potential difference. Now, why is that? How do we understand this? Well, we understand that Q is equal to C delta V. So if we put the same potential difference and a smaller capacitance, we will get to a smaller stored charge. If we increase our potential difference, we see that now each capacitor will store more charge, but still less charge than the other one. So we see the capacitance is really telling us about the slope or the capability of storing charge as opposed to the amount of charge that can be stored. So it is not a huge point, but it is something that students often get confused. Capacitance is not capacity. If you want to know how much charge there is on a capacitor, that's what you need Q for. All right. So just to recap, we create a potential difference from a battery over capacitor. The capacitor responds by building up charges. It builds up those charges until there is no longer a potential difference across the capacitor. All right. So how do we find, actually that last point I said was wrong, I'm sorry. It's not that there isn't a potential difference across the capacitor, it's that the potential here is the same as the potential there. Apologize for that confusion. This will make more sense in the next section. So how do we find the amount of charge on a capacitor? Well, if you take a look at your textbook, page 847, section 29.3, you're going to see Kirchhoff's loop laws. And this is the primary tool that we're going to use for this material. And so how does that work? Well, imagine that you were to kind of walk along the circuit calculating how your potential changes. When you get back to where you start, you're going to find that your potential difference from where you started to where you stopped is zero. What does that mean? If you ask what's your energy here and then you come all the way back around, you say now what's my energy, it's going to be the same because you're in the same location. So what we do for a Kirchhoff loop is we pick any point in the circuit. You could start here, you could start here, it really doesn't matter. You can go in the direction of the battery, you can go in the opposite direction of the battery, it doesn't matter. I myself find it easiest to start at the negative terminal of the battery and to proceed around in a loop, but you'll see by the end of this that you can really do anything you want. So the loop is just a way of keeping track of the mathematics. So we say, all right, let's add up the potential differences around this loop. Well, the first potential difference we encounter is that from the battery. Then the next potential difference we encounter is that from the capacitor, and then we get back to where we start. So we say the sum of the voltages around the loop are equal to the change from the battery, that's here, plus the change from the capacitor, that's here. And what we know is that the sum of those changes has to be 0. So now, if we go from the negative terminal of the battery to the positive terminal of the battery, we have gained potential. And that's what this plus delta VB here is. We have gained the potential of the battery. And then we're going from the positive end of the battery to the positive end of the capacitor to the negative end of the capacitor. And you learned last week that that's dropping voltage, or that's dropping potential. So we gain potential here, we move around, and we drop potential there. So positive, minus. And then we know that the charge on a capacitor is C delta V. So we can now solve for delta V, plug that in. And what do we see? We see that the volts of the battery minus the potential difference on the capacitor leads to the result that we kind of knew already here. That is, the amount of charge that you store on the battery, in this case, will equal to the capacitance of the capacitor times the voltage difference of the battery. So that is to say, all of this voltage difference is contributing to the amount of charge stored here. What if we make it more complicated? What if we add in multiple capacitors? So now I have a battery connected to 2 capacitors here and back to the other end. So is this a circuit that is in series or a circuit that is in parallel? If you're not sure, I want you to pause the video here and think about this for a moment. Is this a series relationship or is this a parallel relationship? All right. So a series relationship is one in which we have to pass through multiple elements to return to where we start without any choices. What does that mean? Imagine I go here, I come through, I come back, I get here. There was no route I could take that like deviated and somehow missed this capacitor, right? If I had another wire here, that would have been fine, but I don't. So as I pass through the battery, over the capacitor, and back to where I start, I have to go through each of these in turn. Those are then in series. So we look at our Kirchhoff loop here, and again, if this is seeming really kind of over your head, why don't you pause the video, go back, try to do what we just did here for this circumstance. The problem with lectures is they're kind of passive. You watch them, they make sense, and then later you try to do something a little bit different, and all of a sudden you feel really lost. So the advantage of having the video lectures, you can pause it, try to do what I'm going to do, and then see if I do the thing you did. All right. So we set up our loop, we climb our battery, or we go over our battery, we go over our capacitor, and then back to where we start. So our equation is VB plus VC1 plus delta VC2. So that's the change across the battery, the change across that capacitor, change across that capacitor, and back to the beginning. We went from low potential to high potential, so it's positive VB. We went from positive plate to negative plate, that's a potential drop. We go from positive plate to negative plate, that's a potential drop. We plug in what we know for Q's and C's, and now we ask the question, what's true about Q1 and Q2? So I'm not going to elaborate on that anymore other than to say, go back and think about how this charging relationship works here, and imagine now there are multiple capacitors in series with one another. How would that charging relationship change? All right. So we see here that Q1 is going to equal Q2. And then if I tell you that capacitor C1 equals capacitance C2, you get an equation that simplifies dramatically, which you can then solve for the charge. And what you get is that basically the charge now stored on either one of these capacitors is 1/2 CVB. Well, if you remember, CVB was how much charge you would get on a single capacitor. So now what we see is we're storing half as much charge as we had before. And so what we say is that this arrangement of capacitors is half as effective as a single capacitor. Which you might wonder, if I'm adding more capacitors, why am I not storing more charge? And that's a really good question. Hold on to that. We'll come back to it. So what happens now if I expand on to 3 capacitors? So now I have my battery, 1, 2, 3 capacitors, all in series. If you were to work this out carefully like we did above, you would see that you get 1/3 the amount of charge stored on each one of these capacitors. And so the effectiveness of our charge storage is less. All right, let's look at a parallel circuit. In a parallel circuit, we know it's parallel because we have multiple routes through our circuit. One of these is this blue route, right? It can climb the battery, come over, drop the capacitor, and around. Another route is to come up, skip this capacitor entirely, come through this capacitor and back around. And then because it's getting messy, I'll make a separate piece here. I could also have done a loop through this part of the circuit here. Now you might say, can I do a loop if it doesn't go through the battery? And the answer is absolutely, because we're just adding up the potential differences around the loop. There doesn't have to be a battery at all. So as I climb through this, the math was going to work the same way. So I'm going to follow the green loop here. I start here and I have a potential difference across C1. There it is. I then continue my loop and I have a potential difference across C2, right there. I went from low potential to high potential, so I gained gained voltage. Then I went from high potential to low potential, so I lost voltage. And what you see from this is that the potential difference across C1 has to be the same as the potential difference across C2. And this is actually a very generalizable statement that anytime you have 2 paths in parallel, that the potential difference across either path will be the same. So you can use this to your advantage. All right, so this is just meant to be an aid to the normal reading that we were doing, to understand capacitors a little bit more based on your simulation. Some students had questions about what happens to the charge on here as these plates get closer. Hopefully this will help you understand that a little bit more. Right? If Q is equal to C delta V, if you increase capacitance and you keep delta V fixed, then what has to happen? Charge has to go up. If you decrease capacitance and you keep delta V fixed, charge has to go down. You could try a different combination of things. You could say keep capacitance fixed. And if you do that, increasing delta V will increase Q. So this material can be a little bit tricky because you might want to think like, what equation do I use? And it's not always obvious what you do. However, the thing that will never fail you is to write down your Kirchhoff loop and to carefully analyze your circuit. I hope you found this video helpful. Please see us in office hours and in regular class times for more help.